in Daisy, I believe, shown in 1979. It's been a while. The charm has been discovered at Brookhaven, actually 5 years earlier than that. This is not exactly a reconstructed jet, but here you see essentially the signature of a charm quark coming. And of course, here is my mentioning of the Higgs, which you don't measure the Higgs directly, but you see Higgs. This is a Higgs to BB bar candidate, and there you see here essentially these things are the remnants of the beauty quarks. Another thing, because I mentioned beyond standard model, the green is not showing up greatly here, but I did not make this plot. This is one proposed Feynman diagram from a group of proposed dark matter combined with supersymmetry signatures. And here, I think the Chi's are in fact dark matter candidates. Another example, and here on this slide, please don't question me too much because I'm still getting used to spin physics to begin with, but the proton spin puzzle is one of the most compelling reasons that RIG is running, that RIG has a polarized spin program, because a polarized collision program. RIG is the first and only collider in the world that can polarize protons and collide them with each other. And one of the things that they have discovered is that about 40% of the spin of the proton is carried by gluons. That doesn't sound like much, but I mean, you just expect, okay, we have 3 quarks in there, one up, one down, okay, that's the spin of the proton. That's not the case. You have 40% are roughly in the gluons. The valence quarks with the C quarks more or less cancel out mostly, and then you have a contribution from the spin orbit. What's also neat to know is pretty much all of the mass of the proton, if you just add up the quarks, it's almost nothing. And it's dynamically generated by the strong force, by the gluons inside. But we know almost nothing about the gluons. We know very little about how they are distributed inside the proton, but how they carry this spin. And here's one measurement from STAR from a couple of years, from I think this year's, is a symmetry between dijets, between hard partons again, giving us some information about how these gluons divvy up the spin between them. And of course, the quark-gluon plasma, which for us is typically generated in a collision of high energy, of ultra-relativistic heavy ions. It may also exist inside a neutron star. I think 1 or 2 people here might be astrophysicists, so it might combine a thing here. The one thing that you can't do that we can do is shoot stuff at it. And the stuff that we shoot at it essentially, and those are again our hard quarks and gluons. So here is sort of the cartoon picture of what happens once we create this QGP. There's also a hard collision somewhere, and a quark gets generated somewhere, hopefully near the surface. One side goes out, behaves like we like them to. The other one goes through this fireball and experiences all of this strong force, radiates away gluons, loses energy. And the rate of this energy loss gives you some information about the transport properties, about the temperature, about the size, about the way that things are deflected. This is one of the key probes of the quark-gluon plasma. So the problem that we face if we want to measure all of these partons is that we can't. Nobody has ever seen a parton, nobody ever will see a parton because of confinement. That's the very force that we want to study and the property that we want to study. It's an empiric fact right now. Every particle that we see is color neutral. Some intuitive reasoning, the gluon field forms narrow flux tubes as opposed to the wide field lines that you see in an electromagnetic interaction. And these narrow flux tubes, as you pull them apart, the strength between them grows with energy between them, or rather with distance between them. So by the time that you could, quote unquote, separate them, you have enough energy to create out of the vacuum a quark-anti-quark pair, and you spontaneously form a meson that goes away here. On the other hand, because I already sort of gave that away in the previous slide, asymptotic freedom is proven in QCD. So if you just compress this, you will see actually free quarks and gluons in the limit. That is the whole reasoning why a QGP exists and why it is interesting. So what do we want? We want to measure these partons. That's really what we're interested in. In come 2 protons, out come parton 1, out come parton 2. What do we get?
Instead, this is what we get. So you see here something is coming in and it splits up further. And if the color were a little bit better, you could see all of these flux, these color strings going in between them, and you get a whole bunch of messy hadrons at the end. So we start with the hard parton.
We have the partonic shower, we have hadronization, and there's even more stuff afterward, and finally we end up with hadrons. This is a challenge. It's very challenging, and I note here there's also further obfuscation because you have a detector, and this is a very clean thing. In reality, there's going to be a whole lot of underlying event underneath. I'm going to get to that. But it's also a real great opportunity, because here you have the hard scale. Here you have softer and softer and softer scales. So if you hone in, or if you can look at different jet energies, but you can also look at different branches, hopefully, maybe. And you can see QCD and study QCD at different scales. That is something that goes beyond just what this parton has to offer. So how do we reconstruct these jets? This is essentially what a jet is, a collimated shower of partons. So let me get back to this beautiful plot from 1979. So what they did is they just looked at all of these tracks and they added them up. You have 5 tracks here, you have 4 tracks here, you have 4 tracks here. These are your jets. That's jet finding. I'm done, right? Easy. Well, the reality looks more like this. Here I generated something very clean. That's an electron-proton collision. And yet, this is a circle. That's where I essentially find a jet, and this is where I find a jet. And then you have all of this stuff. What's that? That's the remnant of the proton. You struck a quark, you kicked out a quark, and what's left is also tumbling down the beamline and falling apart. And what's more, it's actually connected to the partons that you're interested in. So even theoretically, you cannot really say this pion belongs to the jet. It might belong in part to the jet, in part to the beam, in part to the other jet. Here are some more events. This is actually one of the tamest examples that you can find at the LHC. This proton-lead collision at pretty low luminosity. And here you have a gold-gold collision at star. Beautiful detector. And you see every single one of these lines is a charged particle. Everything here is more or less a neutral particle. So this whole practice requires very careful deliberation to decide what is a jet, what belongs to a jet, what can you do to actually explain to your theorist what you're doing. One slide on kinematic variables. I'm not sure that I need to go into this too much. Essentially, we're looking at the azimuth, and we're looking at the polar angle. And the polar angle doesn't really work very well because it's not relativistically boost invariant. So instead, you replace it with something that's called pseudo-rapidity, and it behaves. You can add 2 pseudo-rapidities. That's essentially it. Here's a little bit of a translation, so you can see the coverage here of the star detector is about ±1 for best performance, and if you go into the forward direction, it gets weaker and weaker. These tracks you know less about than about these. So then we get to the Snowmass Accord. This is pretty much the first and most important and still very well remembered conference retreat where people sat together, experimentalists from different experiments sat together with theorists and talked about what is a jet. And it probably helped that Snowmass in Aspen is not exactly terribly looking. And it probably started a trend where physicists to this day like to retreat in nice skiing locations. So the agreement reached back then was use this eta phi space, use a definition of distances that's defined on the eta phi space, use a resolution parameter, a radius if you want, of r equal 0.7, and use the so-called cone algorithm. I'm putting a well here because both of these things are no longer really followed very much. But the key point of this whole agreement is you need to agree with each other among experiments and with your theorists what to use, and you need to communicate it to them. You need to include some other details. For example, how do you treat particles that you can't identify, that you don't know the rest math of? And this crucially applies to theorists as well. In theory, your calculation should also use the NTKT algorithm with E-scheme recombination and a resolution parameter of r equal 0.4. So I like this little quote here. A jet is what a jet finder finds. That's really what it is. A jet in the modern sense is a fulfilled contract. You had a specification and this object was delivered. doesn't have to do anything with a hard process. So some important reasons of why we went away from the old cone algorithms is infrared and collinear safety. That's something that you really strongly want. A collinear unsafe algorithm will, you see here, this one little split, or you split slightly differently. In one case, these are pretty much identical physics. And in one case, you find one jet. In the other case, you find two jets. That is really not something that we want. If two things go in the same direction, if they split in your detector, or if you combine two things into one calorimeter cell, you want them to be the same thing. The other problem is if you have just one little soft particle going away, one little soft gluon. Soft particles we miss all the time in our detectors. You also really don't want to have an observable or an algorithm that is sensitive to this. So here are some old candidates, and you see the longer the bar, the worse the algorithm performs in regards to infrared safety. And this is one of the main reasons for the success of the so-called KT family, which I'll come to now. This is essentially right now the tool of choice for everybody. If you talk about jets, it's going to be one flavor of KT, probably anti-KT. I don't want to go through, I actually can go through this a little bit. You take all particles, you form all pairs between them, you calculate some distance, and then you go, okay, and what is the smallest distance? These two I combine, I reorder my list, I do it again and again and again. And at some point, you're going to be closer to the beam than to another particle. That's when you call it quits. And you're done and say, okay, this is a jet. You have a whole history of how this is built up that'll become important later. So as I said, the resulting clusters are called jets in this operational definition. And there is no other definition that you can really agree on. Some word on the distance measures. You can essentially, it's probably not super interesting, you can measure the distance between them as essentially just the literal distance. Don't care whether they're hard or soft particles. You can weight it first so that a hard particle preferentially absorbs things around it. Or you can go the other way with the KT algorithm and have like soft little clusters grouped together and then come together in a jet. This looks like this a little bit. So here's your KT algorithm. That's the amoeba-like, start from the soft and gather it all up. It's very good at really soaking up everything and giving you a good idea of sizes. It's not very good at finding jets that we like as jets. For that, you want the anti-KT algorithm. That really vibes with what we have. Your leading jets will be circular and will have this hard core around them. The Cambridge-Aachen is sort of in the middle. That's the one where you just have geometrical distance. And here's one more older version, the iterative cis cone. That's the one cone algorithm that survived as an IR and collinear safe option. As I said here, cis cone is IRC safe. You could use it. It's just fallen out of favor. It's pretty slow, and pretty much everybody's happy with KT. A couple other options do exist. EEKT is specifically used for E plus E minus collisions, where you just know that you have two jets in there. So you can force it and say, okay, if I know I have two, find me two. Might be interesting also for EP or EA collisions. That's something that I plan to look into maybe a little bit. You could do some deep learning. I have some friends who tried this. It can perform actually very well. But I have to say this is something where I have a problem with really understanding how you can analytically prove IR safety and collinear safety, how you can bridge the gap to theory. I think deep learning is very well suited to things like tagging and identifying, okay, this might be a gluon jet, this might be a quark jet. I don't think it's fully, at this point in time, fully suitable for jet finding. Here's a little example of something that I've been playing with, which is n-jettiness, that starts by just looking at how many jets do I think are in my event. And that actually works very well. So I created some events that had one jet and some that had two jets, and I measured its one jettiness, and you see this nice separation between them. It's something that becomes quite important at an EIC. But interestingly, it also spits out axes. And these axes can be used as a jet finder as well. And here's something I noticed essentially accidentally, that it performs better, that this kinematic is a better approximation in some cases than the classical KT, anti-KT, or pretty much any of the other. This is a pretty cherry-picked range, so I don't know how much, how great this will be in the future, but it's something to consider, especially because we're after precision, 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 and every bit of systematics counts. A word on instrumentation. You need large luminosity and data taking rate. That's where Phoenix always outperformed STAR. You need a hermeticity and large acceptance, which is where Phoenix can really not compete very much. You need calorimetry, hadronic and electromagnetic with good resolution. You need good tracking, and you want fast trigger detectors. Here's your typical LHC example is CMS, and I only had room for one, otherwise I would have put in Atlas as well. Here's STAR as it stands, and here is the warning, there is no HCal in it. We're making do with it very well, and we're all looking forward to S-Phoenix. That doesn't mean that STAR isn't trying its best to really soak up as many jet measurements before S-Phoenix goes online as we can. A word on heavy ion collisions. This is a proton-proton collisions at 200 GeV. You could actually still draw circles almost. And this is the same thing in a central gold-gold event. And that's, again, very harmless compared to the LHC, but it's terrible. This like a 20 GeV jet will sit on 60 plus minus 20 GeV. So you're dominated by background, you're dominated by fluctuations. So first of all, you can subtract a flat background, that's fine. And then you need to do something about the fluctuations. There's a technique called unfolding, which is essentially just on an ensemble base. It inverts a matrix in a clever way and tries to essentially get back from the smeared, measured to the truth. If that's possible, great. Here is pretty much the slide where I expect to start losing people, unless I already have so. This was my first PRL, so I do like to show it. So what we did there is we need to find out, is it a jet or is it not a jet? Because you have fluctuations of 20 GeV all the time. So what we did is we threw everything away that was below 2 GeV. So all of the soft particles are gone. At that point in time, you can actually trust that what is left is a jet. You have thrown away a lot of real jets, but at least what you have left is a real jet. Then you run it over because you do want to know what is in those soft jets as well. So you run it again and then match it. So if I found it here and I found it here, then I know, okay, this was a jet and this is what its soft components look like. So then I can look, okay, what is the difference between the near side and the away side? Because these are always created back to back. And I can calculate its imbalance. So for a perfect dijet, the imbalance is 0. For a perfect single jet, the imbalance is 1. And we did this essentially here in the black spots. This is gold-gold for the hard cores, and for the soft bits added. And then compare that to what happens in a proton-proton collision. So you see here for the hard cores, there is a clear difference between the two. We actually also calculate all kind of p-values and what have you. But you can see by eye that there is a difference. But once you fill it back up, you see all of this energy that you lost at the top is still there. It has not left the area. It's just been transported down. And that was a really great find because at the LHC, you find these jets all the time, the quenched ones. But what wasn't possible until this measurement was to actually still re-find all of that energy. Once in the LHC, once it's quenched, it's gone. It's all over the detector. So with that, let's go to jet substructure. That's my favorite topic of late. So now that we've done all of this hard work and integrated out all of these hadronization effects, all of the problems with it, let's undo it. Let's just open it all up and see, okay, what do the individual pieces look like? So here you have the traditional questions that you want from a regular jet analysis. How much energy is in the jet? How much energy is left? Where did it go? That's pretty much it. You treat the jet as a parton approximation. And in the substructure, you really focus on what happened in the shower. Was it maybe like this, where with few splits, which indicates a quark jet, or a gluon jet, because glue has more colors, so it likes to split more inside a medium or outside a medium. You have a question between, okay, if this opening angle, if it's very narrow, then essentially the medium cannot resolve it, maybe. And if it's broader, then it can resolve it. So you have the question of, is this decoherent energy loss versus coherent energy loss? Does this two-prong object behave like one, or does it not? And at what point does it do so? One thing that I like is these Lunt diagrams, which I won't go into because they're too detailed, but I would like to point out that I have this. Oh, I deleted a slide, it seems. Okay. Maybe it'll come back. So one of the things that I like to do, one of the earliest things that you can do is this grooming technique that's very, where are we at? Oh, we're doing good. This is really the original thought of, we have this clustering history. We started by combining. Okay, what happens if I take the last combination, these are the two last prongs, and just split them up again, and see how much was carried by one prong versus the other. And if this was just essentially, it just absorbed a tiny little bit, maybe 5% of it was the last addition, then I'm going to throw that away and say that was some wide angle radiation that didn't really belong to the jet. I'm just going to keep the main prong and keep going. And at some point I'm going to stop. And this cutoff point is typically chosen at 0.1. So 10%, you think, okay, that was part of the jet. Anything below isn't. At the end of the day, this is just a number that you communicate to your theorist for the calculation, but it's a realistic number. So, and then smart people went ahead and calculated this through and tried to find what is the distribution. And it turns out, if you do this, then in a particular limit, which is not quite infrared safe, it's not quite collinear safe, but it's the next best thing, it's Sudakov safe, which means that at least the first order, the alpha s squared, the strong coupling constant, goes away. So we become independent of alpha s. What's really exciting, we also become almost independent of PT. This is a universal thing for hard jets, for softer jets. We're independent of whether it's a quark jet or a gluon jet. That's actually a slightly more in-depth argument to make. And this is a connection to a fundamental QCD quantity, which is the Alto-Parisi splitting functions. Those go into any calculation that you do in QCD. If you do DGLAP evolution of jets and what have you, you will find the Alto-Parisi splitting functions. You can directly measure them up to a point. So we did that. So what we find, this is PP collisions, is that nature does a very good job following our models. So you can see here, actually, this is the theoretical curve for Alto-Parisi. It's sort of a 1 over z shape, but it's not quite 1 over z. And for lowish 20 GeV, it falls on it. And it's not perfect, but it does a pretty good job. What's also interesting to note is these are our event generators. Pythia 8 and Herwig, those are pretty much our go-to Monte Carlo generators to describe our data. Now, the interesting thing is the people who did this calculation did so for LHC jets. So they have an overlay like this for generators. And they said, oh, look, above 500 GeV, it all falls on top of each other. 100 GeV, all falls on top of each other. We did this down to 20, 15, and at 10 GeV, it kind of starts really flattening out. But this is a region where people did not necessarily expect perturbative QCD to work. And it does, and it works like a charm still. And it's not entirely clear why. Here you see it's starting to fail. What I'm not showing here is something that I'm sometimes losing a little bit of sleep over. This is with hadronization turned on in the generators. I can turn hadronization off. And then all of a sudden, especially in one generator, I generate something. Without hadronization, there is no ZG. And this to me means this is not happening at the shower stage inside the generator. It happens somewhere in the hadronization stage. It's something I've been in contact with the model creators, and we don't know yet. There might just be something to a universal 1 over z shape that you create from all kinds of things. Maybe this is coincidental that it does such a good job. So at the point that you decided, okay, I've thrown away everything that's soft. My last split is now my ZG number. You also have a distance between them. That's the groomed radius. These are the two orthogonal things that you want to look at. That's something we can also measure. You get it for free. And this is a good approximation or a good feeling for the width of the jet, kind of, not the size, but more of the pronginess. Is it a broad jet or is it a narrow jet? And that's something we measured as well. And you can see here the unfolded data from STAR, going again from 20, 30, 40, up to 40. We can do it above 40, but we're not quite ready to show it. And compared to again, our generators. And here we use Pythia 6. That is the bane of my existence. It's been written in Fortran. It is very hard to compile. The authors almost refuse to help you with the problem because they say, why are you not using Pythia 8? But it's doing a bang-up job, especially in EP collisions and in PP collisions. And then we also have Pythia 8 with the newest tune. We have a Hervik tune that works very well at LHC energies. And you see something that is actually shown in many observables also at the LHC, that these guys tend to bracket the truth. If one of them overshoots, the other one will be underneath. So that is a nice little feature. And it's not quite clear where it's coming from, but it's cool. Here we come back to the Lund plane, because now that I showed you RG, essentially the axes here. So you look at, there's some iterative procedure, but at the end of the day, you make a point for every split in the jet. It's ZG and it's RG, and then people have gone ahead and done this for various various jet quenching models. So how is my jet affected by the medium? This is QPythia. As you can guess, it's Fortran. That's also Fortran, and it's a different version of Fortran. But as you can see, these are very different looking signatures. And most of our traditional, these are tuned to existing data. So all of our traditional measurables are very well reproduced by all of these. And all of a sudden you show this thing, it's like, oh wow, that's a model killer right there. So that's something that I'm very excited about in gold-gold collisions. And I'm curious to see what can be done in maybe E-gold collisions. The big challenge in gold-gold collisions is the background. You still have this fluctuating background. That's something in PT or energy you can kind of handle. Once you go to these more substructure variables, you really get into trouble. Here you see sort of the truth in PP and the truth once you generate something in PP, and then you throw that right into a gold-gold background, some kind of thermal background, just to see what the fluctuations are doing. And you see, well, yeah, there's a bit of a correlation here, but you don't get to see this two-dimensional picture in a measurement. You only get to see essentially this. And once you integrate this all out, much of it goes away. So that's something that you have to struggle with if you want to measure RG in gold-gold. I don't have time to go into what we're doing about that. My friends are going into more or less using a different variable. There's other tricks that you can do. Everything you do here becomes, any substructure, this is really the challenge also. Unfolding becomes multidimensional. You need to have a response for PT and for Z and for RG. All of a sudden, all of these matrices blow up. You need more and more Monte Carlo and machine simulations. You have much more sensitivity to the soft background, because if you have just a little bit of a soft thing here, you don't have quite this collinear safety and this infrared safety in many of these variables. This is, don't want to go into it too much, but it's my pet peeve. What is the truth level for unfolding? Because at the end of the day, your response comes from a training. And for that, you feed your machine something. So you train it on Pythia jets. So you know at some point in time what your detector does to a Pythia jet. That works very well if all you're looking for is PP. But in gold-gold, then you're also biasing yourself to essentially a Pythia jet. You're looking for something that is like a Pythia jet. That's not really the case. This is the acceptance or the efficiency for STAR for certain particles, and you see it drops like a rock at low PT. So all of these soft particles often get lost. not so much a problem for the PT of a jet because there's not much energy in there. But for something like the jet mass or the RG, that is very sensitive. And really treating this quenched jet with lots of it quenched down as if it were a Pythia jet is a problem. With that, let's go to something more fun and uplifting. The near future. S Phoenix is around the corner. And you see here this beautiful picture of an outer HCal, an inner HCal, and then all of the nice things that we had before, except there's also a better vertex detector, and the TPC is faster, and all of that. And these fantastic projections of what S Phoenix can do, and 100 billion events. I'm happy that we have 4 billion right now. This is really, it's a game changer, and I'm very much looking forward to 2023 when it will turn on. So you see here a little bit the timeline, or the line. I wish the colors were a little bit better. So you see essentially what exists right now in these hash marks. I hope that you can see them. And what Rick will do in 2023, 2024 using S Phoenix. And you see what LHC can do and LHC will be able to do. And you see that we start to overlap in many of these things. So the bottom range of the LHC will be covered by the top range of Rick, which is an important thing to really combine things. This is a terrible photo in this particular instance of HCal tiles that were tested at Georgia State. So it would be very rude of me not to point this particular thing out. I'm particularly excited about this because I actually think that low PT is better for substructure than high PT. I always say that TV jets are fantastic, but they're essentially like a pencil. There's almost no substructure to find here. So here I've plotted this delta R or RG, essentially the width between the two prongs for Rick level jets. So that's a very soft one that goes here. And you see it harden up, and as they get harder, they get narrower. And for our range of 40 to 60 GV, that's realistic, we still end up here. And now let me put over this. This is essentially where LHC jets live. And this is the size of a calorimeter tile from the LHC. So this is why they have to throw pretty much everything away that is below here, which is where most of their jets are living. That's a problem that we really don't have with our soft jets. So there are some unique strengths at Rick. We can do jet geometry engineering, which is, I haven't gotten into that very much, but essentially varying these cuts that I used in this AJ analysis I showed a while ago, like the 2 GeV cutoff. You can make that harder or softer, and you can sort of steer in and out your jet into and out of the medium. You have a tight correspondence between the parton and the jet. That's plotted here. It's essentially what was the parton and what was the PT of the jet that we found here. This is the simulation for Rick. This is the same simulation for the LHC. So you see, okay, we found a jet. We don't really know what it corresponded to in PT. Where, as I said, sensitive to this substructure, there's high luminosity and there's an enormous amount of flexibility. We're right now colliding at 11 GeV. Next week, we're going to go to fixed target mode. We've collided gold, uranium, copper, aluminum, whatever you want. We can do it. So we have a very ambitious program of the traditional first, second generation observables. That's all of these CGs, groomed, and what have you underway. And we're trying to rub as much as we can of that at STAR. And we're also all excited that S Phoenix is near, and we want to do this with more precision, more data, and with an HCal. That brings me to the not so far future. It's 10 years. And on the 9th of January, while we had our EIC group meeting at BNL, all of a sudden somebody said, wait, stop for a minute. Can you pull up this website? Which is when the US Department of Energy finally announced that not only was the electron-ion collider approved and declared mission critical, CD0, but also was announced that Brookhaven National Laboratory was selected as the site. So this is the room about maybe 5 minutes once we had gathered after all of this. So in one slide, the physics goals of the EIC. You should also read this probably about 100-page document. It's fantastic. But the key question that we want to answer is how are the C quarks and gluons distributed in space and momentum inside the nucleus, inside the proton? Their spins, their helicity. How does the nuclear environment affect the distribution of quarks and their interactions in nuclei? This is the difference between looking into a proton or shooting electrons at a gold ion. And here's something that I get interested in because of my connection to jet quenching. Where does the saturation of gluon density set in? So what we've seen so far is if you go deeper and deeper, you look further and further, gluons just keep rising, keep rising, keep rising. It has to stop somewhere because there are not infinitely many gluons. So at that point where it ends, people usually think about, that's the saturation regime. People usually think of it in terms of, often think of it in terms of a color glass condensate. It's a sort of a sheet of color that you hit and interact with. That is something that I think could be modeled maybe in some way similarly to jet quenching inside a hot medium. It's a very different physics, but many of the parameters, many of the methods should apply. I should show the final EIC design, so we will be able to use the existing facility and get hadrons of up to 275 GeV. That is for protons, because we have 510 GeV center of mass as our maximum. This is right around where we can get the protons, and probably about 100 to 120 for ions. We can have electrons up to 18 GeV, so we get 18 on 275, that's a nice hard range. This is sort of this is the center of mass energy that corresponds to. This is where I will be living most of the time because this is where the jet region is. The further down you go, I mean, if you have only 40 GeV available in your collision or 20 GeV available in your collision, I will not be finding any 20 GeV jets going in and out there in large time. But it means, so what you see here is the luminosity, how many of these collisions can be delivered. And you see that we span this entire range of the people have helpfully generated these bubble plots of showing, okay, this is how much we need to find QCD at extreme parton densities and saturations. This is what we need for the internal landscape of the nucleus. This is spin and flavor structure. You want to be more differential, and that's kind of the curve here. This is not the winning curve. Ours is the winning curve. And some detector concepts. That's going to be very interesting to see as well. That's essentially, one of them is proposed to be a day one detector. Take S-Phoenix as it is and give it a lot of forward instrumentation. It can be plopped and is ready. What's very nice about it is that Geon simulations, all of that stuff exists for it in a way that doesn't for any of the other ones. This is the other BNL concept, BEAST. It's actually, I mean, all of these. A detector is, at least these three, they're essentially all the same. You have a good tracker, you have a good calorimeter, you have another good calorimeter, and you have a strong magnet to shape them. There's one competing one that I find very interesting, which essentially has nothing but calorimetry cells everywhere. 5D or 4D, I'm not entirely sure what this is. I think it's 5D, because it's, yes, 5D. It's like a momentum plus energy plus time in every cell. So you can do everything with it. It's also horrendously expensive, but it would be great. So we're right now working feverishly on yellow reports, which will explore what are our key measurements and what does that mean for a detector requirement. It's only 10 years, and I'm not kidding. People are really freaking out. Time is ticking. This is very critical right now. So my particular field, of course, unsurprisingly, is substructure. So is the jet fragmentation altered by interaction with the nuclear medium, the cold nuclear medium? Is there quenching in the saturation regime? Can we say something about the initial state differences? Here's, for example, something, okay, does it hadronize inside the nucleus or hadronize outside the nucleus? There's a whole bunch of other families that I didn't have any time to go into. The angularity family can be used to separate quark jets from gluon jets. I think also RG will be excellent at separating quark jets from gluon jets. And you can also do leading particle PID to separate quark jets from gluon jets. What you should be doing then is take 3, 4, 5 of them, feed a machine with it, and let the machine make your cuts and tell you, okay, this is 40% gluon, 60% quark jets. Something else that we're working on, I'm not going to explain it. Well, maybe I should. Otherwise, I shouldn't be putting it here. Many of the quantities that you calculate are sensitive to background. And there are some predictions and calculations that say, you know what, if you calculate your jet asymmetry using traditional jets, you get this much background. If you instead use a slightly different way of doing it, if you use, for example, groomed jets, or if you use the so-called winner-takes-all axis, which essentially just latches onto the hardest constituent, then all of a sudden, all of these backgrounds can go down. I've seen some calculations where they go down by a factor of 5. That is unheard of. That is 25 times more data if you really want to do it, if you want to shrink your error bars by a factor of 5. All of these really rely on having a general purpose Monte Carlo generator where you can test out your models. 5 minutes? Okay. That's perfect. So what general purpose Monte Carlos exist? On the electron-proton side, I was at a workshop last year in Hamburg, very nice city and very nice workshop. We have the big three, Herwig and Pythia and Sherpa, which I didn't talk much about because it's much focused on the LHC. But all of these are making tremendous developments in coming back to EP, EA, DIS type calculations because essentially they're starting to get bored with the LHC and they want to see something new. It's a thriving community even beyond these big three. There's a lot of niche generators in between. And then there's the landscape for electron-ion collisions. Right now, there's Beagle. Beagle is great. It's Fortran-based, of course. But it's a great generator. What it doesn't really have is much quenching. It has a quenching model in there, which I think was obsolete probably in 2005 or so. So that's something to improve upon. And as mentioned, I have some connection to Jetscape. So I think Jetscape is in fact an ideal orthogonal candidate to double the number of available general purpose generators, especially because this one is a traditional one. It's essentially from start to end, you give what you want to collide and it spits out a number. And there's very little that you can steer in between. Jetscape goes very differently. Jetscape wants to give you modules at every point in time. You can say, okay, I have an idea about jet quenching, but I know nothing about how hard processes are generated. I know nothing about hadronization. Well, you can go ahead and write a module that is maybe this many lines of code, plop it in, and keep everything else the same. So I'm not a theorist, but I do play one on TV, and now also on the archive. So this is me in very dark, in the enormous, fantastic cinema museum in Venice. This is a parallel session. This screen is about 5 times my height. It's amazing. It's incredible. And here I was happy to announce the first release of Jetscape 1.0. So I had a natural collection of using Jetscape and developing in Jetscape because essentially I wrote most of the framework part. So I sat down and tried, okay, let's see what we can do for EIC. What changes do you need to make? So we have a large collaboration of experimental and theoretical physicists. That's the cool part. We have computer scientists in there. We have statisticians in there. And we have lots of connections also to large data storage, all of these things that you need. Good funding from the NSF, 43, 45 authors. Essentially, this is, in a large picture, what I just said in words. It's a lot of modules that you can plop in at any point in time, at any stage of the collision, but it's made for quark, gluon, plasma. Well, that really just means that mostly you need to take away the most computationally expensive part, which is hydro, because there is no hydrodynamically evolving medium in a cold nucleus. Instead, you have to put something in that you think happens in a nucleus. And there's a bunch of bookkeeping things that I spend more time on than I want to think about to really understand how the initial stages are generated and parsed. So what I did is I tried to do it in EA. There exists no electron-ion data right now, except for fixed target. Back in DAISY, they were colliding electron-electron, electron-proton. But there was one detector that said, okay, you know what, as our interaction point, we can just put some gas into the interaction region. So they put some krypton in there, some helium, some neon, some xenon. So there you have your one data point for EA collisions. So how do you model this? Well, people did this a while ago with essentially mostly pen and paper. But it's based on pretty much the same physics that I used as the main module in a Monte Carlo way in Jetscape. So I thought, okay, let's try this, put it together. This is my very first attempt at doing this. I do see some quenching. I see much less. This is what comes out of Jetscape. This is what the measured data is. It's a bit confusing here because they have offsets in here. This is what the actual suppression looks like. So this is very promising. I'm not 100% sure why it doesn't quench as much as I thought it would. I think it has a lot to do with that they did some more clever things about the medium length in the original one. That's something that I'm working on right now. But I believe that's a good way forward. And with that, let me just stop. I think I'm right on time almost. So jets have a long history. The first plot I showed was from, I think, 1974, but 79 was the one where you started talking about it. And there's a complete explosion right now of substructure techniques, of jet finding, of all of this. And these are all ways to find really new and orthogonal ways to explore the strong force. To not just look at the parton itself, but also look at the shower inside and look at all of the QCD that happens in the middle. I spend almost no time talking about the LHC. That's not because there is no jet physics there, quite the contrary. There's probably enough to fill an entire afternoon just to get the broad concepts communicated. But I had to make some selection here, and I selected what I know most about. So, as I said, the present is very bright. The near future is very bright with S Phoenix, and for me, very frighteningly not so far future is also very bright with the electron-ion collider. I encourage all of you to maybe take a look to the other side and see what nuclear physics and high-energy physics is all about. Thank you.